take a peek at my first graph. Now I have this labeled on the x-axis as A, and let's just suppose here's B, and let me go straight up to the curve. Now if I draw a line past these 2 points, because I know 2 points on the line, or at least 2 points on the curve, I can compute the slope of that line. Now because locally speaking, at these 2 points, my line crosses it, I don't refer to this as a tangent line, I refer to it as a secant line. Now to come up with a slope is a piece of cake. This is just 9th grade elementary algebra again. So the slope of that secant line is merely going to be rise over run, or shall I say, the difference in 2 y values divided by the difference in their corresponding x values. Well, look at my graph. If this point and this point have x coordinates A and B, then here are their coordinates. Therefore, this is the rise. This is the run. Now, I could likewise have done something a little bit different. How about over here? Excuse me. Instead of talking about another position on the x-axis, let's just move to the right, h units. If I do, I'll plant my feet here. Here are the coordinates, excuse me, of the 2 corresponding points in the graph. Excuse me. Here is the secant line passing through my curve at those 2 points. And its slope is easily determined. Rise over run. Notice how my denominator simplifies quite nicely. Now, I sometimes refer to these 2 fractional expressions as difference quotients. I sometimes refer to this one right here as a Newton's quotient, but I typically have an x instead of an a. We'll get to that. What I want to do next is this. Using my 9th grade algebraic skills to come up with the slope of this tangent line, I completely fall apart. I can't do it because technically speaking, I only have 1 point, that one. I need 2 points to determine the slope of a line with my 9th grade algebra skills. So here's what I'm going to do. Imagine what's going to happen if this point moves along the curve closer and closer to that one, while this one remains fixed. My secant lines are all going to change. They're going to converge onto that blue tangent line. Well, that sounds like a limiting process. So numerically speaking, if I merely take the limit of this difference quotient as b gets closer and closer to a, then the slope of that secant line is going to get closer and closer, numerically speaking, to the slope of the tangent line. So the slope of the tangent line can now be interpreted as the limit of this difference quotient as b goes to a. Or shall I say over here, this is a little nicer because h is an actual quantity. So if I take the limit as h goes to 0 of this difference quotient, that too will give me the slope of the tangent line, at least at the value of x, which is a in both these cases. So, oh, I didn't draw the picture, did I? There's my tangent line. There's how I can interpret this slope. Now, I gotta confess, back in pre-calculus, this didn't merely always represent the slope of a secant line. This also represents the average rate of change of f over the interval of a to b. So now you can think of this as representing the instantaneous rate of change of f with respect to x at x equals a. Likewise here too, that could be interpreted as an average rate of change, but this is going to represent our instantaneous rate of change of f with respect to x at x equals a. But that means if I can interpret the slope of the tangent line as instantaneous rate of change, it sounds like it got multiple interpretations of what this limit really represents. And since I'm getting tired of talking, let's just cut to the chase. Man-made definition. From now on, if I see this thing right here, or this thing right here, to remove any interpretation of what it represents, I'm going to give it a new name. I'm going to call this the derivative of f at x equals a, and I'll refer to this the same way, just a different way of representing the derivative of f at x equals a. I have numerous notational schemes to label these two things, and I'll get to that before I'm finished today, but for now, let me just introduce one symbol representation. To represent the derivative of f at x equals a, I will write f of a, but I'll put what I call a prime symbol above the f.